Um, so just to start off, I study the unsteady aerodynamics of wing gust encounters. And before I go into that and what we do exactly, I'm gonna give it like a small motivation. So in the past like a decade or so, there has been lots of research into designing micro air vehicles and drones and all that stuff. And because of the advance of manufacturing techniques, we've been able to go smaller and smaller. The problem with going smaller and smaller in the design of air vehicles is that uh, you end up basically entering the low Reynolds number regimes or aerodynamic regimes where the flow easily separates. So in conventional aircrafts, the flow of air is big, and like the wings and the vehicles are big enough to where they are easily uh, in the high Reynolds number regimes where the flows can have more energy to stay attached to the wings. But in smaller scales, um, the physics of flight is a lot different because of the fact that flows easily separate. So you actually need to be able to and work with flow separation and unsteady aerodynamics to generate lift rather than fight it, because you really can't. So a huge problem in flying, for example, smaller air vehicles or drones. I mean, I don't know if you try to fly a drone, but they're very susceptible, like a little drone, but they're very susceptible to windy weather, or even if you're like buildings and all these uh, structures that sort of cause like shear layers and unsteady sort of wind flows that could tip your vehicle over, cause it to lose stability. So that's sort of a motivation of trying to understand the unsteady aerodynamics of flight, is to be able to design better and more stable smaller air vehicles. But it also goes into designing larger air vehicles that are more resistant to bad weather conditions. I mean, usually most of the time, if there's like a storm or something like that, the flights get canceled because planes cannot fly in like unsteady weather conditions. So that's another motivation to why we want to do this. So again, this is sort of a CFD picture of what the flow structure could look like under unsteady conditions. You have flow separation, you have the formation of a leading edge vortex, you have lots of shedding and sort of chaotic flow physics that affect the experienced lift and affect the forces on the wings. So to be able to sort of design these vehicles, we need to really understand and get a better grasp of the flow physics. So with that said, the main objective of my research is to first understand the unsteady flow physics of gust encounters. So we're focusing on basically studying what happens in the flow and the aerodynamics of a wing encountering a large transverse gust, so a large vertical gust. And then using this understanding, can we mitigate the impact of the gust? For example, can you use some sort of kinematic maneuver or pitching to try to cancel out the lift transients you get from encountering that gust? And to tackle this question, we are using two different techniques. We first do experiments and we also do simulations. Um, but since the focus of this class is experiments, I'm going to focus on the experimental part. Um, so with that said, this is our test facility. So to study aerodynamics, we use a water tow tank facility located in the manufacturing building, which if you don't know where that is, it's sort of close to Xfinity Center. It's where the helicopter is. Um, so the sort of the overview of the facility is shown here. To start off, this is a picture of the water tow tank. It's around 23 feet long to give you a sort of a rough scale of the size we're talking about. In the water tow tank, we have a sort of a motor carriage that where you can mount a wing and sort of move it in the water to simulate motion. So lots of people use wind tunnels or water tunnels where you are moving the flow. Instead, we are moving the wing in this facility. So for example, you have sort of a linear inductive motors here, like sort of like your roller coaster motors that move this entire structure to the right to sort of simulate the forward motion of the wing. And then you have vertical control rods here where you can actually move them up and down to pitch the wing. Now, so we use that method to simulate the motion. The way with which we simulate a gust is basically by generating a water jet in the center of the tunnel. So we have this water pump over here that takes in water from one side and blows it up vertically upward in the center of the water tank. So using sort of the setup, you have the pump here, the wing, the gust generator. There's like a honeycomb over here, and from the honeycomb you have vertical water jet going upwards, sort of like similar to your, I don't know, like if you've been in a hot tub and you have like these water jets that blow water on your back, it's sort of similar to that, but it's blowing water upward. And we use that to simulate the gust. Now, the two data acquisition techniques we use to sort of probe the physics in our experiments is using a force sensor. So we put a force sensor on the wing to measure the aerodynamic loads on the wing. And we also use particle image velocimetry, as Andrew said, to sort of look at the 2D flow slice around the wing to see what's happening in the flow as the wing sees the gust. And please feel free to interject with questions as I go on. If something wasn't clear, just let me know. This is all what I wanted to say about this slide. So here's an example. I'm going to show two PIV experimental setups that I've done in the past to sort of show you what we're dealing with here. In this experiment, I wanted to look at the flow of the aerodynamic flow around the wing encountering a gust. So this is sort of the setup. So this sort of cross section shows the water tank, and this is one end of the water tank. We have our laser coming out of here. There's a telescopic lens, which is basically a lens that you can vary the focal length of to sort of resize the beam cross section as you want. We have a bunch of mirrors over here where the laser bounces off, and then there's a final mirror here where the laser is shot down the tank. So just to give you an idea, this is basically towards this end of the tank, and we're shooting the laser down here to the gust, which is shown here. Now, once the laser gets to this structure here, which is right above the gust, we have again a series of mirrors that sort of takes the beam and directs it 90 degrees downwards. And then you have a Powell lens, which Andrew talked about in the last lecture, that takes this narrow laser beam and fans it out to a laser sheet. So you can see the laser beam here. The Powell lens takes this laser beam and spreads it out into a laser sheet. So you can actually image the 2D plane. Now the gust is coming out of this gust generator. You have a high-speed camera on this sort of side that's looking straight on the laser sheet. And then we tow the wing sort of into the gust to look at the flow. So this video is an example of one of the cases of the gust encounters I looked at. Now the video here is taken and blurred out so that instead of seeing particles, you see streaks. So if you instead of showing like frames in time, you can take maybe every 5 frames and sort of average them out. And when you average 5 frames out, you can sort of see the streaks to show the particle motion. So you can sort of see a rough streamline of the flow by averaging sequential frames and making it into one frame, and then do that to every other 5. And you can sort of play the video like that. So without further ado, this is an example of the encounter. You have the gust coming out vertically from here, and this is a flat plate or our wing that's sort of coming in at a 0 angle of attack. And as you can see here, as once the wing encounters the gust, you see the roll up of flow around here that creates a leading edge vortex. You also see deflection in the gust and stagnating flow at the wing. And then you see the vortex separates and the wing and leaves out the wing and convects backward as the wing moves forward. Now, you can take sort of the actual particle images and again do the sort of correlation that Andrew talked about to actually extract velocity vector. So the great thing about this measurement technique is that you can get quantitative data from the flow field rather than, I mean, if you do like flow visualization or other types of flow viz, you can see the flow and how it's going, but you can't really extract any numbers from it. So here you can do correlations across sequential frames of the particles to actually extract out the velocity. So in this video, I'll show you, again, same thing, wing encountering the gust. I think it's also the same case where the velocity vectors are shown with black arrows, and the colors red and blue are vorticity sort of contours. So blue is, I think, negative vorticity, and red is positive vorticity. And vorticity is essentially just a measure of flow circulation. If vorticity is positive, then you have sort of a anti-clockwise. So it's sort of the sign on the vorticity measures the direction of rotation of the flow. And this is useful to actually look at the leading edge vortex structure because it's a vortex, there's high vorticity in the vortex region, so we can easily look at the vorticity in the flow field to demarcate where the vortex is and where the vorticity is being generated. And vorticity is directly related to circulation, which is again directly related to lift. So again, this is sort of the same video. You can see the blue sort of region marking the generation of the vorticity. And then as the wing moves through it, the vortex grows bigger and separates out as the wing moves through the gust. Now, the second setup I wanted to show is of just doing PIV on the gust itself. So the reason I was doing that is we did a redesign in our gust generator. You can see the redesign here to make it a lot more sort of to get better flow quality. So rather than just having sort of a pipe going to a settling chamber with lots of stagnation flow and the water shooting upward, we sort of made the gust generator a lot more streamlined, a lot more like a wind tunnel, basically with turning vanes, flow conditioners, screens, all that stuff. In this setup, instead of going from the end of the tank, I'm coming from below the tank. So you have the laser head here, which generates the laser. And this setup, for just your information, is basically under the tank. So this laser head is connected to a telescopic lens. This telescopic lens, again, sort of, you can use it to focus or refocus the beam to get the sort of the size that you'd like. The sort of the size of the cross section of the beam that you'd like. Now, the size of the cross section affects the laser sheet in that it affects the thickness of the laser sheet that you get. You also want to focus the laser beam down such that you get most of the laser beam through the Powell lens, which fans out the laser beam to the laser sheet. So you don't want like a really big cross section where most of the laser is lost and not being sort of gone, or it's not going through the Powell lens to create the laser sheet. But also you don't want to focus the beam too much to where you can break lenses, which I've done. At one point I was sort of focusing the laser beam, and I happened to focus it to too small of a region to where the power density in that region was really high, and I cracked the power lens. So sort of a cautionary tale. So you have this telescopic lens,
How much did that mistake cost, just out of curiosity?
$250,
Okay.
which is not that bad. Like for I've done worse.
Yeah, we have a joke in our lab that you're not really a member of the lab until you cost Dr. Rowley $1,000 in some equipment that you broke in.
Oh, that's fair. Like for
That's a
example,
common experience in grad school.
yeah. Like I mean, this high-speed camera is like 60K. So
Yeah.
you break that, and then this laser beam again is probably really expensive too. Anyway, so you have this telescopic lens shooting the beam down. The power lens is right here. So laser beam comes in this way and sort of fans out to a laser sheet. The laser sheet hits the mirror, okay, and the mirror sort of reflects the laser sheet upward into the tank, which you can see here. So this is the laser sheet. And then you have the camera here. It's a phantom camera, which again it's pretty expensive, but that's because you can get upward like 2,000 frames per second, if not more. I don't remember exactly the numbers off the top of my head. Like if you've watched these, like I don't know if you watched like the slow-mo guys or people on YouTube that take really slow motion footage. This is basically the camera that they use. So again, moving on. Now, this is an example of of data you'd get from the gust generator. So the gust generator is somewhere down here, okay, and it's shooting flow upward, and you can see here the particles moving with the flow. So you can take the images, sequential images of the particles motion and the gust, and sort of correlate them to get velocity contours. Now, the red and blue here shows the vertical velocity magnitude. So red means higher velocity magnitude in the vertical direction, blue means lower. So you can see that towards the edges of the gust, there is no flow. So because we're operating in a water tank with quiescent fluid, but once you get in the gust region, you see like lots of sort of high vertical velocity because of the gust generation. So that's an example of a way we'd use to characterize the gust that's being produced. All right, this I think Andrew went over all these sort of slides with you, so I'm just gonna again go through it but really quickly. This is a flow visualization similar to the one I showed you earlier with the blurred images of a wing starting from rest. So that's why it starts off slowly and builds up velocity. You can see here, you can easily sort of, he either did a convolution or he averaged images, but you can sort of change the particles into particle streaks to see clearly the streamlines. And then from here, you can see the vortex. You can also see secondary vorticity that's happening on the wing, and then the vortex sort of starts shedding away from the wing. You also see a trailing edge vortex, which is really cool. You can see the streamline clearly. So again, for even not just quantitative data, it's even for like if you want to get like a qualitative sense of what's happening in the flow, it's super useful. Anyway, yeah, you got the support over there, you get the suspended particles coming in, and you have the free stream coming in this direction. All right, moving on. Again, not a new thing. Basically, you can just get like a bunch of images, average them together, and you can start seeing the streak where the ball is moving, right? This is a schematic of the general schematic of what a PIV system involves. You have the laser over here. Again, this is sort of a like an optical setup so that you can have the right laser beam cross-section size. This is like basically the telescopic lens that I showed you before. You have a mirror, and then you have a power lens that takes the beam and spreads it into a laser sheet. This laser is connected So you have the laser system, the high-speed camera, and the computers are all connected to a synchronizer or a high-speed controller. And the job of the synchronizer is basically to synchronize the laser and the high-speed camera so that they fire at the same time. Otherwise, you have the laser sheet firing and then stops firing, and then you'll have the camera taking a picture. They'll be out of sync, and then the camera will take no pictures with the laser. So you need the laser and the camera to fire at the same time so that you can actually take laser images. And everything goes into a computer that sort of does the high level control and does the post processing. And also you can also vary the options, like you can vary the exposure of the camera, you can vary the intensity of the laser, you can vary other stuff related to the image acquisition. Now, this is an example of a laser that we use that's currently under repair. It's an LDY300. Basically, what's happening here is you have two lasers, laser 1 and laser 2. So both of those are two separate lasers. These lasers are directed using sort of mirrors, like really precisely positioned mirrors, so that they end up firing from the center. So like, for example, let's take this laser, the beam goes like this, reflects through this mirror, reflects through another mirror, and goes out the center. Same for laser 1, takes a similar track so that it fires from the same sort of position on the laser. Now, the reason for having two lasers is that sometimes you need to do really high speed imaging for the correlation. And there are lasers that, for example, you can't really pulse the laser at an arbitrary frequency. Every laser has a limitation on the frequency you can pulse it at. For example, the laser I used, which was not this one, the one earlier, the green laser that I used, has a maximum pulse frequency of 15 hertz. So it physically cannot do more than 15 hertz pulsing. But what if you need to image flows where the correlation will only work if you have like 200, 300 hertz pulsing frequency? Then you can use two lasers instead of one, so that you can fire the two lasers slightly out of phase to get the delta T that you'd like between the two lasers to get good correlations. So you'd have, for example, each laser is firing at a 15 hertz frequency, but then one of the lasers is tiny bit fires slightly out of phase of the second one, so that you can effectively get a 200 hertz rate between the two lasers, if that makes sense. So this is the reason why most PIV lasers have two laser cavities rather than one. However, if you have a really high frequency laser that can fire with the required frequency to get good correlation between sequential images, then you don't need two lasers. You can only fire one laser and fire it at the required frequency, sort of at the required pulse frequency. So this computer does data acquisition, image pre-processing. For example, a very common image pre-processing that you'd like to do is to remove the background image from your laser, from your images. Sometimes you have the laser sheet coming out and you have like glass or ladders or whatever things in the background that show in the images. So if you take that image, if you take all the images you've taken, you average them all up and subtract out that average image, you end up with images that are a lot more, that don't have that background. So you'd end up with images with purely seed particles and nothing else. You do the PIV cross-correlation, vector validation, and post-processing to get vorticity or to get whatever flow quantities you'd like to get. Example setup. Andrew went over that, so I'm going to skip it. He went over that too. I'm going to go again over this. What's the concept? You have seed flows in the particles that move with the flow, right? You have a laser light that sort of eliminates the field of view that you're interested in. You have high-speed photography that take images fast enough so that you can effectively track the particles. So if you have a camera that doesn't have a high frequency, you could have a really high particle displacement. You'd have a particle here, and then once the second image is taken, the particle's somewhere over there. If that's the case, then you're gonna really get bad correlations because the particles are not close to each other. So you need high-speed photography so that you take fast enough images so that the particles have moved, but haven't moved too far, so you can get realistic velocities in your correlations. And then you basically, again, take image 1, image 2, and if you know where the particle went, and you know the delta t between consecutive images, you can get speed by using u equal to distance over time. And this is, again, an example of the product of what you get, which is basically a velocity vector. So the advantages of that, the field, you get a whole field image. So for example, there are other flow measurement techniques like hot wire or like what was it called? Like laser interferometer, and LDI. And for like a problem with these imaging techniques, or sorry, not imaging, but more like measurement techniques, is that you can only get one point in the flow. In PIV, you can get the entire flow field. So that's a huge advantage with PIV that is not, for example, available in hot wire measurements. You can get the entire flow field and not just a point in space. It is also non-intrusive. If you want to use a hot wire, for example, a hot wire probe to get the velocities at a point, you're going to have to put an actual hot wire probe in the flow, which will affect the global flow condition. So it is intrusive. However, PIV, if you use the suitable particles to seed the flow, is non-intrusive. So you're effectively getting the actual flow field that you would get if you wouldn't have any measurements at all. And then it's instantaneous. So you can, I mean, depending on the camera that you use, the laser that you use, you can get time resolved PIV. You can resolve really, really small structures in the flow. You can get turbulence measurements, turbulence intensities. So it's a very powerful technique. All right, so PTV versus PIV, Andrew went over that. So practically speaking, PTV is where you take a particle and you track it. PIV is where you take instead of like separating the flow out to particles and tracking the particles, you take the flow and you separate it out to windows in the field. And each window can have, 5, 10 particles, it doesn't matter. And then instead of actually tracking one particle, you effectively track the average of all the particles in that window. So in that sense, because you're doing an average of all particles rather than tracking one particle, it's a lot more accurate. So PTV is old school, PIV is more new school with better algorithms, better cameras. So cameras with a lot more high resolution in them and high speed. It's statistical, which makes it a lot more robust than doing PTV because it's a statistical method that relies on the average of a bunch of particles rather than one particle in space. Seeding, in wind tunnels, you'd use gases or oil droplets that are atomized or smoke to sort of seed the flow. In liquids, it's a lot easier to seed liquids because you can get particles that are just naturally buoyant in the liquid, and you don't have to consistently sort of spray seeding into the flow using an atomizer. You can just put the seeds in the liquid, stir it up real well, and if your seeds or particles are buoyant enough, they're gonna just stay buoyant in the flow. So you can there's a bunch of different ones. Examples here are silver coated glass spheres, or any glass spheres that would scatter light effectively so that they glisten in the laser. You can also use fluorescent particles, which is really nice. So fluorescent particles, they don't just scatter light, but they also create their own light in the laser, which is very nice if you have lots of background problems. If you have if you have a background that's really hard to subtract out, then you can use fluorescent particles that glow a lot better than particle seeds. And since they glow a lot more, you can they over dominate the background, so you don't get much of a background problem in your image if you're using fluorescent particles. So what makes a good seeding? What makes a particle a good candidate for seeding the flow is that it must follow the flow, which means that it must be similar enough to the flow to where it actually follows its motion even when there are high gradients in the flows. It should be able to follow the flow. So a Stokes number is a measure of how good a particle can track the flow. So yeah, it describes how well particles follow the flow, and it is defined as tau p over tau f. Now, tau p is the particle timescale, which in a more practical sense, it's a scale of measure to measure how effective a particle tracks the flow. So for example, a high particle timescale, that means that the particle has so much inertia that if you sort of push it around, it takes a while for it to get up to speed, like a really, like a big truck that requires, you pushing on the gas for a bit just to get it going. That's a high inertia. So any particle that has high inertia has also a high particle timescale. Now, tau fluid is the fluid timescale, which is like the same timescale, but for the fluid you're using. So a low timescale for example, viscous fluids have high inertia and thus high timescales. Any forcing you give the fluid, it will take time to respond. But low viscous fluids, gases, they have very low time response. You force it, it goes right away. It doesn't have this inertia that you have to overcome. So yeah, now that's basically a general description of what these timescales are, but this is more of a technical definition of the timescale. People use viscous drag for particle timescale. For example, a particle that has high viscous drag has a high timescale. If you have a high viscous drag, that means you have a high resistance to motion, right? Because of that drag, that gives you a high timescale. So in a sense, imagine you have a flow and imagine you have a wind tunnel, okay, and you turn the wind tunnel on. So you have zero flow and you turn it on, you immediately have some 50 meters per second. That response or time scale basically is a sort of measure of, okay, once you turn on the wind tunnel, okay, how long will it take for your particle to get up to speed? A particle that takes a while to get up to speed is a particle with a high time scale. A particle that, just that immediately follows the sort of the forcing velocity has a low time scale. So this is a formula for how to, for example, calculate the time scale of a particle. But in summary, the lower your Stokes number is, the lower your particle timescale is, the better you'll be able to track the fluid. So you need to pick the particles so that you have a low enough inertia in your particles that it's capable to track the fluid. If you have a high inertia in your particles, they'll start having their own dynamics and they won't track the flow and you'll get garbage measurements. And an example of what time scale you'd want to choose for your particles is if you, in your lab, you have a cylinder that's shedding vortices, right? You can use the vortex shedding frequency to obtain that time scale. So you look at the frequency of the shedding, the time period of your shedding is 1 over f. That's your fluid time scale. So you pick the particle time, you pick out particles that will give you that have a time scale such that the Stokes number is low enough for the fluid to track, for the particles to track the fluid. So yeah, again, this is sort of a summary of what I was saying. If the Strohal number is a lot less than 1, the particles will follow the fluid. So you need to pick an experimental condition where the Stokes number is low. Illumination, which is again a very important aspect to PIV. You can technically use any light sheet you want. You can use an LED, you can use a light bulb, but we always use lasers because they're a lot more easily controllable. First of all, lasers are very consistent in their illumination intensity, so you're not going to get lots of variation in the amount of light in your light sheet, which would be a problem for your experimental data because, again, you're going to get garbage correlations if you have varying intensities in your light sheet. So it's easy to control. You can easily, since it's like a narrow laser beam, you can easily shape it. And you can easily shape it into a laser sheet with a thin thickness. Now, the reason you'd want a really thin laser sheet is if you're doing two-dimensional flow measurements, that means you need to track particles in your plane and not other plane. If you have a laser sheet that's really too thick, your camera is gonna see too many particles that are not in your plane of interest. So you're gonna get spurious velocities that you're not interested in. And again, a laser can be easily pulsed. You can easily also get really high frequency lasers, and you can control how fast they pulse, and you can also sync it with the camera. So these are basically the advantages of using a laser over, say, an LED source. So this is a rough schematic of what your laser sort of optical setup would look like. You have this laser head that is shooting out the laser. Now the laser beam hits a bunch of optical sort of lenses or a telescopic lens or something to reshape the beam so that you get the right size of beam hitting your Powell lens or your fanning lens. So these are focusing lenses. You can focus, defocus the lens so that you get the right beam size. You hit a mirror. The mirror basically reflects the laser into another direction to hit the Powell lens, and then the Powell lens takes that beam and fans it into a sheet. And here is an image of what a Powell lens would look like. So the beam goes in here, right? And it hits this edge, and basically this edge focuses the beam and then fans it out like so. And then an important parameter you need to look at when picking out the Powell lenses is the fan angle. So the size of the laser sheet is a function of the fan angle of the Powell lens. If you want a really wide laser sheet, you need to pick a Powell lens with a really high fan angle. But if you don't need a wide laser sheet, but you need a laser sheet that has a high intensity, then you'd want to fan less. So you want a lower fan angle. Now, Powell lenses range from like 5 degrees to like 45 degrees. So you have a really wide selection. They're also really expensive, so don't break them. Imaging schemes. Yeah.
And I'm just going to hop in for 1 second since we're up at the end of class time. You don't need to, end. If you want to continue talking, then it'll all be recorded and everybody can view it afterwards. But I want to let everybody know that it will be recorded. So if you have to leave for a next class, feel free to do so.
Oh, I apologize. I'm going to try to see if I can speed up here. All right, the next couple of slides, I'm just going to go over them in less detail. Imaging schemes, again, you have double frames where you can correlate pairs of images. And that is if you have a low speed laser. But then if you have a high speed laser, right, which we talked about earlier, you can instead sort of correlate all the images together. So you can, if the delta t between like the pulsation of one laser is too high, you can't really correlate those two images. But you can again fire the two lasers out of phase so you can get pairs of images that are close together. Then you can correlate that. But if you have a high-speed laser, then you can get the required delta t between all the images, so you can sequentially correlate 1 to 2, 2 to 3, 3 to 4, so on and so forth. Again, time resolved a huge amount of data. Now, computing displacement of the particles is kind of technical, so I'm just going to skip that for now. But basically, the basic premise is that you take two windows in so you take the same window, but at two different times, okay? And then you take the first window and you start shifting it around until you get the first window to match the second window, right? So you have the first window here. This is the second window. So this is window, well, this is, let's say this is one window, but this is at T1, the black image, and at T2, the red image. You get the first image and you start shifting it around until you get the best match with the window in T2. Once you get the best match, you look at the shifting that you had to do, and this is your particle displacement. And you know delta t, so you can calculate the speed at this point in time. So this is just a highlight of the correlation, and I'm going to skip all that because, again, this is much math. So Andrew will post all these slides on the website, and if you have any questions about the later slides, just free to email me. This is an example of the wing with particles, and this is what the correlation would give you. You get velocity vectors, and you can clearly see the vortex and such. And you have to do some post-processing on the vectors, which is called outlier removal. If you have vectors that are completely off, you need to remove them. And the way you find out if a vector is like completely off from what it should be is that you look at the vectors around it. If the vector in the middle here is way too different than the vectors around it, then you replace it. And again, the technical way of doing it is that you look at the median of the vectors around the spurious vector or the bad vector. And if the bad vector is like 3-4 standard deviations away from the median of the vector surrounding it, then you replace it with the median. But this is basically the way you do it. And again, this is a video of an example of what it would look like after you cross-correlate all the images together and post-process. Is you'd be able to get vorticity contours with really high fidelity and really high resolution and time as well. So these are rules of thumb. I'm not going to go over them. But if you have any questions regarding them, please let me know. There are different versions. The 2D PIV is nominally what we do at our lab. You can also do 3D stereo PIV with 2 cameras. You can also do tomographic PIV, which I believe is look at an entire volume of fluid rather than one plane. But 2D is the most basic one, and that's about it. Please feel free to ask me any questions.